All we can see is a tiny island of light in an ocean of darkness. We have mapped billions of galaxies within our cosmic horizon, but this is not the whole story. This video is a journey to the absolute frontier of reality, where you will learn what modern physics truly says exists beyond the edge of everything we know. We will confront the possibility of infinite copies of yourself, universes floating like bubbles in a void, and the chance that our entire world is a cosmic illusion. The ultimate boundary might not be a place but a limit of our own perception. Are you ready to question the very nature of existence? To grasp what lies beyond, we must first understand where the edge actually is. It is not a physical barrier in space, not a great wall or a shimmering boundary you could ever visit. Our edge is made of something far more profound, time itself. Because light has a finite speed, we can only see the parts of the universe from which light has had the time to travel to us since the cosmos began. This creates a vast but finite sphere around us known as the observable universe. From our vantage point, it stretches for about 93 billion light-years in every direction, containing every star, every galaxy, every photon that has ever reached our telescopes. This is our entire cosmic reality, everything we have ever known or measured. But here is the crucial point: this observable sphere is not the universe. It is simply the part of the universe we can see. The true, total universe, what we call the unobservable universe, extends far beyond this horizon of light. We have no way of knowing if it just goes on a little farther or if it stretches out forever, truly infinite. So the edge is not a place in space, it is a horizon in time, a limit to our vision. And beyond that horizon, the real adventure begins. Think of a ship sailing away on a perfectly calm ocean. As it moves farther out, it seems to sink lower and lower, until finally its hull vanishes below the line where the sea meets the sky. That ship hasn't crashed or been destroyed, it has simply sailed beyond your horizon, the limit of your vision caused by the curvature of the Earth. Our cosmic horizon works in a strikingly similar way, but with a far more bizarre twist. The galaxies at the very edge of our observable universe are not just far away, they are being carried away from us by the expansion of space itself. And for the most distant ones, space between us and them is stretching so fast that they are, in effect, moving away from us faster than the speed of light. This is not science fiction, and it does not violate Einstein's rules because it is space itself that is expanding, not the galaxies moving through space. The consequence is profound. Light leaving one of those ultra-distant galaxies, fighting its way toward us through the expanding fabric of the cosmos, is like a swimmer trying to cross a river that is widening faster than they can swim. They make progress, but the far shore keeps receding. For those galaxies beyond a certain critical distance, their light is fighting a losing battle. It will simply never, ever reach us. That distance marks our ultimate cosmic horizon. It is not a physical wall, but a fundamental boundary to information, a permanent curtain drawn across reality. Everything on the other side of that curtain is, and always will be, completely and utterly unknowable to us. We can infer it must be there, but we can never see it, measure it, or interact with it in any way. Our island of light has a permanent, unbreakable shore. This raises a profound question about the nature of that unobservable expanse. Is it truly infinite, or does it eventually curve back on itself? To find the answer, we need to discover the shape of the universe itself. Think of it like this. You can have three basic geometries for space. First, a flat universe. This is like an endless, perfectly flat sheet of paper. Parallel lines stay parallel forever, and the angles of a triangle always add up to 180 degrees. If our universe is flat, it is almost certainly infinite, stretching on without end in all directions. Second, a spherical or closed universe. Picture the surface of a balloon. It is a finite space, but it has no edge. An ant walking on that balloon could travel forever in a straight line and never fall off, eventually returning to its starting point. In such a universe, parallel lines would eventually meet, and a triangle's angles would add up to more than 180 degrees. Third, a hyperbolic or open universe. This is shaped like a saddle or a potato chip. Here, space is curved outward, parallel lines would rapidly diverge, and a triangle's angles would add up to less than 180 degrees. Like a flat universe, a hyperbolic one would also be infinite, so the shape is everything. It tells us whether we live in a finite cosmos, a self-contained bubble of reality, or an infinite, unbounded realm. For decades, scientists have been measuring the cosmos with exquisite precision, looking for any sign of curvature, and the results are both definitive and mind-bending. The measurements are in, and the geometry of our universe is flat. Not just a little flat, but perfectly, astonishingly flat to the limits of our ability to measure. This is the conclusion from decades of data from satellites like Planck, which mapped the faint afterglow of the Big Bang. That cosmic background radiation shows no detectable curvature at all. It means if you draw a triangle across the cosmos with sides billions of light years long, its angles would still add up to exactly 180 degrees. The simplest interpretation of this flatness is that the universe is infinite. It just goes on and on without any edge or boundary forever. But there is another, more subtle possibility, a cosmic loophole that changes everything. What if our universe is not infinite, but is so unimaginably vast that its curvature is too slight for us to detect? This is the model of a finite but unbounded cosmos. Think of it not as a flat sheet, but as the three-dimensional surface of a four-dimensional sphere, a hypersphere. The idea is tricky, but the analogy is familiar. Consider the Earth. Its surface is two-dimensional. You can move north, south, east, or west, but not up or down into the air. That two-dimensional surface is finite. You could walk around the entire planet. Yet it has no edge. An ant on a beach ball never encounters a cliff or a wall. It just travels in a loop. Now, inflate that idea by one dimension. In a three-dimensional hypersphere universe, the three dimensions of space we experience are like the two-dimensional surface of that ball. Space is curved, but in a higher dimension we cannot perceive. In such a universe, if you could build a starship and travel in a perfectly straight line for an almost incomprehensible length of time, you would not sail off into a void. You would eventually, after circumnavigating the entire cosmos, return to your starting point from the opposite direction. You would have looped the universe. There is no outside in this model. The universe is not embedded in some larger empty space. It contains itself. All of reality is the surface. So is our vast, flat-seeming cosmos actually this colossal, self-contained bubble. If it is, then the journey beyond the edge becomes a journey that eventually leads you right back home. But if the universe truly is infinite, then we must confront a possibility that reshapes our understanding of reality itself. An infinite cosmos does not just mean more stars and more galaxies. It means that, given an endless expanse, every single arrangement of matter that is physically possible must occur. Not just once, but an infinite number of times. The laws of physics are like a cosmic rulebook, and there are only so many ways to arrange particles within those rules. In an infinite universe, you run out of unique arrangements. You are forced into repetition. Somewhere, at a distance so vast it defies all comprehension, there is a galaxy identical to our Milky Way. Orbiting an identical sun is an identical Earth, and on that Earth there is a person who is, in every conceivable atomic detail, you. They are reading a script identical to this one, on a device identical to yours, in a room that mirrors your own. They have lived every moment of your life, made every choice you have made, and are pondering this very same idea at this exact same moment. This is not speculation about parallel universes or other dimensions. This is a direct, logical consequence of infinity within our own universe. The scale of it is paralyzing. That other you is not a few galaxies over. The average distance to your nearest identical copy is likely so enormous that if you wrote the number of light years as a 1 followed by zeros, the string of zeros would be longer than the observable universe itself. They are forever beyond any possible horizon, eternally isolated. Yet they must exist. The philosophical weight of this is staggering. It means your life, with all its unique joys and sorrows, its specific triumphs and regrets, is not unique at all. It is a template repeated endlessly across the void. Every possible variation of your life that the laws of physics allow also plays out. A version where you took that different job, a version where you said yes instead of no, a version where history took a slightly different turn. Infinity accommodates them all. It turns the universe into a cosmic library containing not just every book ever written, but every book that could ever be written. The silence of that infinite space is not empty. It is filled with echoes of every possible story, including your own. The sheer weight of infinity is already almost too much to bear, but the story does not end there. Modern cosmology suggests an even stranger possibility, one that makes our infinite universe seem almost quaint. What we call the universe may not be the totality of existence at all. It might just be our local neighborhood, one bubble in a frothing sea of cosmic foam. This is the multiverse, born from the leading theory of our cosmos's explosive birth, cosmic inflation. The idea is that a fraction of a second after the Big Bang, space itself underwent a period of hyper-fast, exponential expansion, stretching a subatomic speck into a cosmos larger than our observable horizon in an instant. But what if that inflationary process never truly stopped? What if it is eternal, a driving force of reality that continues in most of space, only occasionally and randomly slowing down in certain regions? Wherever inflation slows and ends, space stops stretching so violently, energy condenses into matter, particles form, and a stable universe like ours is born. This region becomes a bubble universe, floating within the still inflating, faster-than-light expanding background. And if inflation is eternal, this process happens not once, but an infinite number of times, creating an endless, bubbling multiverse. Each of these pocket universes is causally disconnected from the others, forever separated by oceans of inflating space that expands faster than light can cross it. So the edge of our observable cosmos, that horizon of light and time, might be just the inner wall of our local bubble. Beyond it is not more of our universe, but the inflationary void, and beyond that, an infinity of other universes, each with its own unique destiny. This is where the possibilities become truly alien. When a new bubble universe forms, the way inflation ends can be random, like a spinning wheel landing on a number. That random landing can determine the fundamental laws of physics within that bubble. The strength of gravity, the mass of an electron, the number of dimensions, even the speed of light could all be different. In this cosmic landscape, our universe is not special. It is simply the one where the numbers came up right for atoms, stars, planets, and life to form. We are living in a bubble where the physics lottery produced a winning ticket. There could be bubbles where gravity is so strong that stars form and collapse in minutes. Universes that are nothing but empty, dark voids because forces never congealed into matter, or realms with 4 dimensions of space where creatures we cannot even conceive of build their civilizations. The multiverse is not a theory of everything. It is a consequence of our best theory for the beginning of everything. And it suggests the ultimate beyond is not a place of more stars, but a fractal infinity of entirely different realities, each forever out of reach, each with its own edge, its own story, and its own version of the question, what lies beyond? Yet another possibility redefines the edge not as a distant horizon, but as a wall right beside us. This idea comes from the depths of string theory, a framework that attempts to unify all forces of nature. In this radical view, the three dimensions of space we experience, length, width, and height, are not all that exist. There could be additional, hidden spatial dimensions, curled up so incredibly tiny that we are utterly unaware of them. But what if one of these extra dimensions is not small? What if it is vast and our entire universe is just a three-dimensional slice floating within it? This slice is called a brane, short for membrane. Imagine our reality as a single, impossibly thin sheet of paper. That paper is our brain. It contains all the particles and forces we know, trapped within its three-dimensional surface. Now picture that sheet of paper floating inside a vast, empty room. That room is the bulk, a higher dimensional space that exists beyond our perception. We, as creatures of the brain, are like drawings on that paper. We can move left, right, up, and down on the page, but we have no concept of and cannot move into the room around us. The edge of our universe in this model is literally the edge of the page, but here is where it gets truly strange. In that higher dimensional bulk, our brain is not alone. Other brains could be floating out there, each one its own entire universe with its own laws of physics. And because they exist in the bulk, they could be astonishingly close. Another universe, a completely separate cosmic story, could be a mere millimeter away from ours, but that millimeter is not a distance we can travel in our three dimensions. It is a separation in a direction we cannot point to, a dimension we cannot move along. We are like characters in a book on a library shelf with another book pressed right up against our cover. The stories inside are utterly separate, the characters forever unaware of each other, yet they physically touch in a higher spatial dimension. This means the ultimate frontier might not be billions of light years away. It could be right here, all around us, a barrier of dimensionality. The edge is not a place you sail to, it is a direction you cannot face. A collision between our brain and another in that hidden bulk could have been the Big Bang itself, or could spell a future cosmic transformation we cannot foresee. In this view, the question of what is beyond the edge has a chillingly simple answer: another universe, so close we could almost touch it, yet separated by the deepest gulf imaginable, the gulf of perception itself. There is a theory that pushes the boundaries of reality to its absolute breaking point. It proposes that everything you see, feel, and experience, every star, every planet, every thought in your mind, might be nothing more than a magnificent illusion. This is the holographic principle. The idea is deceptively simple, yet its implications are universe-shattering. It states that all the information contained within any region of space, like the entire three-dimensional volume of our cosmos, can be perfectly encoded on its two-dimensional boundary. Think of a hologram like the kind you might see on a credit card. That shimmering, three-dimensional image is not truly three-dimensional. It is projected from a flat, two-dimensional surface etched with microscopic patterns. The holographic principle suggests our universe operates on the same cosmic scale. The three-dimensional world we inhabit, with all its depth and solidity, could be a projection from the two-dimensional surface that surrounds it, the ultimate edge of space itself. In this view, the boundary is not a place you look out from, but the source code from which you are rendered. Every event happening here, in the apparent volume, is just a translation of information stored on that distant, enclosing shell. You are not looking at the edge of the universe, you are looking out from it, a three-dimensional shadow cast by a two-dimensional reality. This turns our intuition inside out. The true reality, the fundamental layer of existence, would not be the spacious world we move through, but that incomprehensibly dense, information-packed surface at the edge. Your entire life, every memory, every sensation of the sun on your skin or the weight of an object in your hand would be data written on that cosmic film. It is a notion that makes the solid ground beneath your feet feel suddenly, profoundly fragile. If this is true, then the quest to understand what lies beyond the edge becomes a different kind of journey altogether. We are not searching for more space, but for the projector. The universe leaves its fingerprints in the cold. To peer toward the ultimate edge, we must look back to the very beginning, to the oldest light in existence. This is the cosmic microwave background, a faint, cold glow that permeates all of space. It is the relic radiation from a time about 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and light could finally travel freely. That primordial light has been stretching and cooling for over 13 billion years as the cosmos expanded, and today it reaches us as a microwave whisper, just a few degrees above absolute zero. To our telescopes, it appears as a nearly uniform map of the sky, a snapshot of the infant universe, but this map is not perfectly smooth. It contains tiny, rippling variations in temperature, the seeds from which all galaxies and cosmic structures would later grow. These are the universe's baby pictures, and by studying them, we are essentially looking at the most distant surface we can possibly see, a fossilized horizon from a time before stars. This map is our most powerful tool for understanding the shape, size, and origin of everything. Yet, within this ancient echo, astronomers have found something deeply puzzling, a feature so strange it challenges our understanding of the cosmos itself. In the vast, speckled tapestry of the cosmic microwave background, there is a region known simply as the cold spot. It is an unusually large and frigid patch of sky, a place where the ancient radiation is significantly cooler than the surrounding average. At first, scientists thought it might be a statistical fluke, a random clustering of cold pixels in the data, but repeated, precise observations have confirmed it is real. It is too large and too cold to be easily explained by the standard model of the universe's evolution. It is an anomaly, a cosmic bruise on the oldest surface we can observe. If the CMB is a fossil map of our universe's infancy, then the cold spot is an unexpected scar, a mark that does not seem to belong. Its existence demands an explanation, and the most mundane answers are falling short. Could it be a vast, empty region of space, a supervoid between galaxies so enormous that light loses energy crossing it? Perhaps, but the scale of void needed to create such an effect seems improbably large, challenging our models of cosmic structure. The persistence of this mystery has led some cosmologists to propose a far more radical idea, one that connects directly to our journey beyond the edge. What if the cold spot is not a feature of our universe at all, but a mark from outside it? In the context of the eternal inflation multiverse, where our cosmos is one bubble among infinite others, a collision between neighboring bubbles is a real possibility. Picture two soap bubbles floating toward each other in a sink. When they touch, their boundaries merge and create a disturbance at the point of contact. Now inflate that idea to a cosmic scale. If our universe, in its earliest moments of inflation, gently bumped into another separate universe bubble, the energy of that collision would have left an imprint on the fabric of our nascent cosmos. That imprint would have stretched with the expansion of the universe, fossilizing into a distinct anisotropic pattern on the cosmic microwave background. The cold spot, according to this extraordinary theory, could be the cosmic scar from that long-ago encounter. It would be a bruise on the edge of our domain, tangible evidence that there is something beyond the inflationary void and that we once touched it. This is not just theoretical speculation, it is a testable hypothesis. Scientists have searched the detailed patterns of the CMB for the specific signatures such a collision would leave, like concentric rings of temperature variation around the cold region. The data is tantalizing but not yet conclusive. The mere possibility, however, reshapes the cold spot from a curious flaw in the data into a potential window. It transforms that ancient cold patch of sky from a fossil into a message, a whisper from a neighboring reality that tells us our bubble is not alone. The edge of our observable universe, imprinted on the CMB, might not just be a boundary of light, but a wall that once shuddered from an impact on the other side. But the cosmic microwave background is not the only place where the edge seems to whisper to us. There are forces at work on a scale so vast they bend the motion of our entire galaxy, and their source remains one of the deepest mysteries in modern astronomy. Our Milky Way is not drifting through space in isolation. It is part of a grand, flowing river of galaxies, all being pulled toward a specific point in the distant cosmos, a region with such immense gravitational pull that it defies easy explanation. Astronomers call it the Great Attractor. This mysterious gravitational anomaly lies in the direction of the constellation Centaurus, about 250 million light-years away. Its pull is so powerful that it is drawing our entire local group of galaxies, along with thousands of others, toward it at a staggering speed of over 2 million miles per hour. For decades, the true nature of the Great Attractor was hidden from our view because it lies directly behind the plane of our own Milky Way, a zone obscured by thick clouds of interstellar gas and dust. It is like trying to see a distant city through a dense, perpetual fog. With the help of X-ray and radio telescopes that can peer through this cosmic murk, we have begun to map this region. We now know the Great Attractor is not a single, monstrous object, but an immense concentration of mass, a dense knot in the cosmic web known as the Norma Cluster, surrounded by hundreds of thousands of galaxies. This supercluster is massive, but here is the puzzle. Its gravity alone does not seem sufficient to account for the full force of the pull we feel. Our motion is too fast, too urgent. It suggests there is something even larger behind it, something with far more mass, exerting its influence from an even greater distance. This realization points to structures of almost incomprehensible scale, forces that operate on the canvas of the entire observable universe. And to understand the full picture, we must also consider what is pushing us. For every great pull, there must be a corresponding push. Scientists analyzing the grand flow of galaxies discovered that while we are being pulled toward the Great Attractor, we are also being pushed away from an equally vast and eerily empty region of space. This cosmic void, with far fewer galaxies than average, has been dubbed the dipole repeller. Think of it like this: if the Great Attractor is a massive mountain range creating a gravitational downhill slope, then the dipole repeller is an immense, empty valley behind us. The relative lack of mass in that void means there is less gravitational pull holding us back, so the attraction from the dense region ahead becomes the dominant force. We are caught in a cosmic tug of war between an overdensity and an underdensity, between a gravitational peak and a valley. But the scale of these structures is what truly boggles the mind. The Great Attractor and the dipole repeller are not just local features. They are part of a flow that encompasses millions of galaxies across billions of light-years. This grand river of motion suggests the distribution of matter in our universe is imbalanced on the largest scales we can measure, and this leads to a profound and unsettling question. What if the source of this immense pull is not fully within our sight? What if the greatest concentrations of mass, the true engines driving this cosmic flow, lie just beyond our observational horizon in the unobservable universe? The gravitational influence of an object does not stop at the light horizon. A supercluster of galaxies 100 billion light-years away, forever invisible to us, could still be tugging on the fabric of space-time in our neighborhood. The Great Attractor we see might merely be the nearest visible part of a far vaster structure, most of which lies over the cosmic hill, forever hidden. Our motion through the cosmos, then, becomes a clue. It is a fingerprint of the unseen, a hint that the geography beyond our edge is not random or uniform, but is structured by gravitational mountains and valleys of staggering proportion. We are like sailors feeling the pull of a distant current, sensing the presence of a continent we cannot yet see, guided by forces from a shore that lies forever beyond the horizon. The most profound structures in the cosmos are not the glittering clusters of galaxies, but the immense, silent spaces between them. These are the cosmic voids, regions of near-total emptiness that stretch for hundreds of millions of light-years. To fly through one would be a journey of staggering loneliness, where you could travel for 100 million years and see only a handful of faint, isolated galaxies in the vast dark. They are not true vacuums, but they are as close as the universe gets to nothingness. Yet, in their profound emptiness, some scientists see a potential clue to what lies beyond everything. The standard explanation for voids is elegant in its simplicity. In the early universe, tiny quantum fluctuations were stretched to cosmic proportions by inflation, creating a web-like pattern of slightly denser and slightly thinner regions. Over billions of years, gravity acted as a cosmic amplifier. Matter flowed from the thin regions into the dense ones, like water draining from a landscape. The dense regions became the great walls and filaments of the cosmic web, glittering with galaxies. The thin regions were evacuated, becoming the voids. They are the negative space of the universe, the sculpted hollows left behind after creation. But could there be more to the story? Could these colossal pockets of near nothing be more than just drained basins? A radical theory suggests they might be interfaces, places where the fabric of our universe is subtly influenced by an external reality. In the context of the bubble multiverse, where our cosmos is one expanding domain in a higher dimensional bulk, the boundaries between bubbles are not sharp walls. They are complex, dynamic fields of energy. If another universe bubble were to form very close to ours in that primordial foam, its presence could have created a repulsive force, a kind of cosmic pressure that pushed matter away from that region during our universe's infancy. This process would have created a seed of exceptional emptiness, a region that started out with far less matter than average. As cosmic evolution proceeded, this seed would have grown into one of the giant voids we observe today. In this view, a void is not merely an absence, it could be a fossil imprint, a dent in our universe's structure caused by the gentle, repulsive nudge of a neighboring reality. It would be a permanent scar on the cosmos, a place where the membrane of our bubble universe was, and perhaps still is, subtly pressed against the membrane of another. This idea transforms a void from a mere empty room into a potential wall, a shared boundary with a universe we can never see. The silence within a cosmic void, then, is not just the silence of missing galaxies. It could be the silence of a borderland, a place where the laws of our reality whisper against the laws of another, forever separated by a gap we cannot cross. The greatest nothings we can find may paradoxically be the closest we ever get to something else entirely. Dark energy is the silent architect of our ultimate fate. For decades, we believed the universe's expansion, born from the Big Bang, was gradually slowing down under the relentless pull of gravity. Then, in the late 1990s, astronomers made a discovery that shattered that assumption. By observing distant supernova, they found that the expansion is not slowing at all. It is accelerating. Something is actively pushing space apart, and we call that something dark energy. It is not a substance, but a property of space itself, a kind of anti-gravity woven into the fabric of the cosmos. As the universe expands, more space is created, and with it, more dark energy. This makes the push stronger over time, leading to an exponential acceleration that will only grow more dominant. Dark energy now dictates the long-term destiny of everything we see, and in doing so, it is actively forging a new kind of edge, one defined not by light but by isolation. Imagine a future trillions of years from now, where the acceleration has become so fierce that the cosmic horizon tightens like a noose. Galaxies outside our immediate local group will first be pushed beyond the reach of our telescopes, their light stretched into undetectable infrared whispers. Then, the acceleration will sever the gravitational bonds that hold clusters of galaxies together. Our Milky Way will find itself utterly alone in a deepening void, all other island universes having vanished over the horizon of expansion. But the most extreme fate predicted if dark energy grows in strength is known as the Big Rip. In this scenario, the repulsive force does not just push galaxies apart, it becomes so powerful that it overcomes every binding force in nature. First, galaxy clusters are torn asunder. Then, individual galaxies are shredded, stars flung into the endless dark. As the rip intensifies, gravity within solar systems fails, planets are ripped from their suns. In the final moments, the force would overcome the electromagnetic bonds holding atoms together, and then the very nuclear forces inside atomic nuclei. In a final, silent flash, every molecule, every atom, every fundamental particle will be pushed infinitely far from every other. The universe would not end with a collapse or a freeze, but with a total and absolute disintegration of structure itself. This is dark energy's ultimate boundary, a horizon of destruction that moves inward from the cosmic scale down to the subatomic. But even before such a catastrophic end, dark energy is creating a more subtle yet equally permanent edge. As space stretches faster and faster, the sphere of causally connected space around any point shrinks. 2 points in space can only influence each other if they can exchange information at the speed of light. When the space between them expands faster than light can traverse it, that connection is severed forever. Dark energy is accelerating this process, carving the observable universe into smaller and smaller isolated pockets. In the far future, our entire observable universe may contain only the remnants of our own galaxy, with every other bit of cosmic history having receded over a causality horizon. We will be alone, not just in space but in time, unable to receive any signal or evidence that anything else ever existed. The edge of the universe, then, becomes a moving wall of disconnection, creeping ever closer, engineered by the relentless push of dark energy. It asks a haunting question: is the cosmos constructing its own final solitude, making certain that the ultimate answer to what lies beyond is simply and forever nothing? Dark energy carves a future of ultimate isolation, but there is a more fundamental boundary we have yet to confront, one woven into the very fabric of existence itself. To truly ask what is beyond the edge, we must question the nature of the stage on which this entire cosmic drama plays out. We must ask about time. Our entire journey so far has assumed time as a constant river, flowing from a definite beginning toward an uncertain future. But what if that river has a source spring, and what if anything lies beyond its headwaters? According to our best physical models, time as we understand it did not exist before the Big Bang. The event was not an explosion in space and time, but the explosive emergence of space and time. The singularity from which everything expanded was a point where the known laws of physics, including our concept of causality and sequence, break down completely. In that state, the very words before and after lose all meaning. This presents a profound conceptual barrier, one that our intuition struggles desperately to cross. We are wired to think in terms of sequence, of cause and effect. So we naturally ask what caused the Big Bang, what existed before it. But if time itself began then, the question what was before is as nonsensical as asking what is north of the North Pole. You can travel north until you reach the pole, but once there, every direction you face is south. The concept of north simply ceases to exist at that point. Similarly, at the moment of the Big Bang, the concept of before ceases to exist. There is no temporal direction to point in, no past to reference. The question assumes a framework that is not applicable. This is not merely a semantic trick, it is a fundamental limit of our language and our perception. We are creatures of time trying to conceive of a state that is timeless. The challenge is not just scientific, it is deeply philosophical. It forces us to distinguish between two ideas, the universe and reality. The universe, with all its stars, galaxies, and laws, may have begun at the Big Bang, but could there be a broader, timeless reality in which that event occurred? Some cosmological models, like certain interpretations of the multiverse or cyclical universes, attempt to embed our cosmic beginning within a larger, meta-temporal framework. In these models, our Big Bang is a local event within a grander, eternal landscape where time, or something like it, may flow in a way we cannot comprehend. Yet even these models eventually hit a wall. If you propose an eternal cycle of universes, what sustains the cycle across the eons? If you propose a meta-time in which our universe bubbles into existence, what caused that meta-time to begin? We are pushed toward an infinite regression, or we must accept an ultimate, uncaused beginning, a brute fact of existence. The edge of time, therefore, may be the most absolute frontier of all. It is not a place you could travel to because travel requires time. It is not a wall you could touch because touch is an event in time. It is a logical and perceptual horizon beyond which our tools of thought simply fail. To wonder what is outside of time is to try to see with a sense we do not possess. The silence beyond the edge of the cosmos might be profound, but the void beyond the beginning of time is a different kind of nothing. A nothing so complete it lacks even the potential for something. It is the absence of absence itself. There is one final frontier that redefines the edge not as a distant horizon or a temporal boundary, but as a line of code. This is the simulation hypothesis, the idea that our universe, with all its staggering complexity and apparent physicality, is not fundamental reality at all, but an artificial construct, a simulation running on some form of inconceivably advanced computer. If this is true, then every mystery we have explored takes on a new, chilling meaning. The edge of our observable universe, the strange flatness of space, the arbitrary values of the fundamental constants, even the unsettling silence of the cosmic voids, would not be features of nature. They would be artifacts of the simulation's design, limits imposed by the processing power and memory of the system running it. In this view, the Big Bang was not the beginning of everything but the initialization of the program. The laws of physics are not discovered, they are the rules of the simulation's engine, and the question of what lies beyond the edge becomes a question of hardware. What exists outside the server, the simulation argument popularized by figures like Nick Bostrom, rests on a logical chain. If a civilization could ever reach a level of technological maturity capable of creating vast, realistic simulations of conscious beings, and if such a civilization had any interest in running them, then the number of simulated minds would vastly outnumber the biological ones. Statistically, we are more likely to be among the simulated beings than the original creators. It is a modern, technological twist on age-old philosophical questions about the nature of reality. But this is not just philosophy. If we are in a simulation, there should be evidence in the cracks of the code. Just as a video game might have a draw distance, a limit to how far the engine renders detailed scenery, our universe might have computational limits. Some physicists have speculated that the finite resolution of space-time, hinted at in theories of quantum gravity, could be exactly that, a pixelation of reality at the Planck scale. The speed of light might not be a fundamental constant of nature, but a processing speed limit, the maximum rate at which information can be updated across the simulation's grid. Even the mysterious, finely tuned numbers that govern our universe, like the strength of gravity or the mass of an electron, could be parameters set by the programmers, values chosen perhaps at random to see what kind of universe would emerge. Unexplained glitches in physics, anomalies that stubbornly resist all conventional explanation, would be the most tantalizing clues of all. They would be like finding a texture that failed to load properly in a game world, or witnessing an object clip through a wall, a brief glimpse of the underlying logic breaking down. The cold spot in the cosmic microwave background, or certain quantum effects that seem to defy local realism, could be viewed through this lens not as cosmic scars or fundamental mysteries, but as bugs in the code. The most profound implication, however, is for the edge itself. In a simulated reality, there is no outside in a spatial sense. The entire simulated universe is data. The edge is where the simulation stops processing, where the data ends. It could be a hard boundary, like the edge of a map in a video game, beyond which there is only a void or a repeating texture. Or, more intriguingly, it could be a functional limit. Perhaps the simulating system only renders the parts of the universe that are being observed, a cosmic version of the tree falling in a forest with no one to hear it. The distant, unobservable universe might not be rendered in full detail because no conscious being is there to perceive it, saving immense computational resources. In that case, the edge is not a place but a rule of efficiency. The entire cosmos beyond our causal horizon might exist only in low resolution, like a blurred background in a photograph, its details filled in only if and when we could ever get there. This transforms our quest from a journey through space to a detective story within our own perception. The ultimate frontier is no longer a distant shore of stars, but the user interface of reality itself, and we are both the players and the characters, searching for the exit command in a game we did not know we were playing. The simulation hypothesis suggests the universe might be a construct, but physics offers its own portals to elsewhere. If the cosmos has an exit, it may be hidden in the most extreme distortions of spacetime itself, in the theoretical twins of black holes. We are familiar with black holes, regions where gravity is so intense that nothing, not even light, can escape their event horizon. But the equations of general relativity, in their beautiful symmetry, also permit the existence of their perfect opposite, white holes. A white hole would be a region of spacetime from which matter and energy can only erupt, never enter. It is like a black hole running in reverse, a cosmic fountain of infinite pressure where everything is expelled. While a black hole is a one-way street into oblivion, a white hole would be a one-way street out of somewhere. No one has ever observed a white hole, and many physicists believe they are mathematical curiosities that cannot form in our universe. Yet they persist in theory as a tantalizing possibility. If they do exist, their origin is a profound mystery. One compelling idea is that a white hole could be the other end of a black hole, connected by a tunnel through the fabric of spacetime. This tunnel is a wormhole. Imagine the universe as a vast sheet of paper. Two distant points on that sheet are separated by a long journey across the surface. But if you could fold the paper, bringing those points together, you could punch a hole straight through, creating a shortcut. A wormhole is that shortcut through the higher dimensions of spacetime. It would be a bridge or a throat connecting two separate locations. In theory, a wormhole could link two places billions of light years apart in our own universe, making interstellar travel conceivable. Even more fantastically, the two mouths of a wormhole might not connect locations in the same universe at all. One mouth could be here, and the other could open into a completely different cosmos, a separate bubble in the multiverse or a brane world floating in the bulk. In this scenario, a black hole might not be a final grave, but a tumultuous entrance ramp, and a white hole could be the chaotic exit, vomiting matter and light into an alien reality. The journey through, however, is the problem. The wormholes permitted by our current equations are notoriously unstable. They would snap shut in an instant unless held open by a form of matter with negative energy density, something exotic that creates gravitational repulsion. We do not know if such exotic matter can exist in the required amounts. Furthermore, the forces inside would likely be catastrophic, shredding any structure into its fundamental particles. Yet, the mere theoretical possibility reshapes the map of reality. It suggests that the edges and boundaries we have been contemplating might not be impenetrable walls, but gateways, if only we could find the key and survive the passage. The universe's most forbidding prisons might in fact be its secret doors. Perhaps the Big Bang was not a unique creation event, but a rebirth. This is the core idea of cyclic cosmology, a family of theories that replace a single, lonely beginning with an endless cosmic rhythm. In these models, the universe has no ultimate start or finish. only an infinite series of phases, each ending in a transformation that seeds the next. The edge of one cosmic era is not a void but a transition into another. One of the most compelling versions is the ekpyrotic model, a name derived from the Greek word for conflagration. It begins with our universe as a three-dimensional brane, floating in a higher dimensional bulk, just as we explored earlier. But here, there is another brane, a parallel universe, floating a microscopic distance away in that hidden dimension. These two branes are drawn together by a force across the bulk, moving on a collision course over eons. When they finally meet, the impact is not destructive but creative. The immense kinetic energy of the collision is converted into heat, radiation, and matter, flooding our brane with an explosive surge of energy. This collision, this brane smash, is what we perceive as the Big Bang. In this view, the hot, dense state from which our universe expanded was not a singularity, but the aftermath of a cosmic kiss. The entire history of our cosmos, all 13.8 billion years of star formation and galaxy evolution, is just the long, cooling aftermath of that primordial encounter. And what happens next? The two branes, having bounced off each other like sheets of rubber, move apart, stretching and cooling as our universe expands. But the attractive force between them remains. Eventually, the expansion slows, halts, and reverses. The branes are pulled together once more, setting the stage for another collision, another Big Bang, another universe born from the ashes of the old. This creates a cyclic model, a universe with no beginning and no end, only an eternal oscillation between bang and crunch. The Big Crunch is not a final collapse into oblivion, but a reset. As the branes approach again, the universe contracts, galaxies merge, temperatures rise, and eventually all structure is smoothed out into a hot, dense plasma, perfectly preparing the conditions for the next collision. It is a cosmic phoenix perpetually dying in fire to be born again. This elegantly sidesteps the thorny question of a beginning of time. There is no before the first Big Bang because there was no first one, only an endless cycle stretching infinitely into the past and future. So what then is the edge? In a cyclic universe, the spatial edge we have been searching for might be an illusion. The true boundary is temporal, the moment of the crunch and the bang. To cross that boundary would be to witness the universe reborn, to see the laws of physics themselves reset and reconfigured. Each cycle might be similar, but it need not be identical. Perhaps the fundamental constants, the number of dimensions, or the very laws of nature are slightly shuffled with each rebirth, creating a cosmic natural selection where only cycles that produce stable, long-lived universes like ours can persist. We could be living in just one iteration of an infinite series, our particular set of physical laws nothing more than a winning ticket in an eternal lottery. This vision transforms the cosmos from a one-act play into an endless epic, where every ending is a new beginning, and the greatest mystery is not what lies beyond the edge, but what came before our dawn and what will follow our long, cold night. But all these grand theories, from cosmic cycles to simulated realities, share a single, silent assumption that there is an objective universe out there to be discovered, independent of us. What if that assumption is wrong? What if the most fundamental frontier is not made of space or time, but of mind itself? This brings us to the most intimate and perplexing edge of all, the boundary of consciousness. We have been searching for what lies beyond the cosmos, but we must also ask, does the cosmos only exist because we are here to see it? This is not mere philosophy. It is a question that emerges from the coldest, hardest data in science, from the quantum realm. In the world of the very small, particles do not have definite properties like position or momentum until they are measured. An electron exists as a cloud of probabilities, a shimmer of potential spread across space. But the moment a scientist sets up a detector to observe it, that cloud collapses. The electron snaps into a definite location, as if forced to choose by the very act of being seen. This is the famous observer effect. It suggests that at the most fundamental level of reality, the universe does not settle on a concrete state without an interaction that constitutes an observation. The word observer here is tricky. It does not necessarily mean a conscious human. It can mean any interaction that leaves a record, any irreversible transfer of information. But the line is blurry, and it leads to a profound unease. Could consciousness itself play a role in crystallizing reality from a sea of possibilities? Some interpretations of quantum mechanics, like the Copenhagen interpretation, essentially say that reality is not fully real until it is measured. It is a radical idea, the universe as a potentiality waiting for a witness. If we extend this thinking to our cosmic search, the implications are dizzying. Could the very act of us looking out into the cosmos, of pointing our telescopes at the cosmic microwave background or measuring the redshift of galaxies, be part of what brings the universe into its current form? Are we not just discovering the edge, but in some subtle way participating in its creation? This blends cosmology with the deepest mystery of all, the nature of our own awareness. We perceive a vast, ancient, expanding universe, but that perception is a flickering signal inside a 3-pound organ, a story constructed from electrical impulses. All of our majestic maps of galaxies, our measurements of dark energy, our theories of branes and multiverses, are ultimately patterns in human consciousness. The universe may be 13.8 billion years old, but our experience of it is always now, always here. So when we ask what is beyond the edge, we must also ask, where does the observer end and the observed begin? Is the boundary of the self the final and most impenetrable horizon? Perhaps the quest to find the limit of everything is also a journey inward, to understand the one thing that makes the question possible in the first place. Physics itself draws a final, uncrossable line around what we can ever know. The cosmic horizon is not just a distant place, it is a permanent information barrier. Because the expansion of space pushes the most distant galaxies away faster than light can travel toward us, their light will never reach Earth. This means any events, any civilizations, any wonders that exist beyond that horizon are forever locked away from our perception. We are surrounded by a sphere of unknowability, a cosmic event horizon that defines the absolute limit of our possible knowledge. No future telescope, no matter how advanced, will ever pierce that veil. The universe beyond is not just far away, it is causally disconnected from us, as separate as if it were another dimension. We can theorize, we can extrapolate, but we can never confirm. This is a humbling truth of our existence. We are prisoners of our own space-time, forever confined to a finite island of light in an infinite sea of darkness. So how do we make any statements about the whole cosmos? We rely on a guiding assumption, a philosophical pillar of modern cosmology called the cosmological principle. It states that on the largest scales, the universe is both homogeneous and isotropic. Homogeneous means the distribution of matter and energy is roughly the same everywhere. Isotropic means it looks the same in every direction. This principle is the reason we can look at our tiny corner of the cosmos and dare to make claims about the entirety of existence. When we see galaxies evenly scattered in our deep field images, we assume that if we could magically teleport to a point 100 billion light-years away, we would see a similar, statistically uniform distribution of galaxies. It is our best guess, our only reasonable guess for what lies beyond the edge. But it is crucial to understand that this remains an assumption, a leap of faith based on the data we have inside our observable bubble. We have no way to test it directly. The cosmological principle is an article of scientific faith, necessary for us to build models of the universe, but forever unverifiable. It could be wrong. The unobservable universe might be wildly different. There could be colossal structures of a scale we cannot conceive, walls of galaxies or voids of nothingness that make our entire observable cosmos look like a speck of dust on a mountain. There could be regions where the laws of physics are subtly different, or where dark energy behaves in another way. We will simply never know. This is the ultimate scientific frontier, not a puzzle to be solved, but a boundary to be acknowledged. The silence from beyond the horizon is not just an absence of data, it is the sound of a fundamental limit. Our quest to understand everything may have to accept that some things are, by the very laws that govern reality, forever beyond our grasp. This human urge to find a boundary is not new. It is etched into our oldest stories. Long before telescopes and satellites, our ancestors looked up at the starry sky and told tales of the world's edge. For the ancient Norse, the universe was a great tree, Yggdrasil, with its roots and branches holding the 9 realms. The Egyptians saw the sky goddess Nut, her body arched over the earth, touching the horizons with her fingertips. In many traditions, the cosmos was an island of order surrounded by a formless, chaotic sea, or a flat disk resting on the backs of elephants, turtles, or infinite pillars. These were not just fanciful myths, they were humanity's first cosmological models, born from a deep need to explain where the familiar world ended and the unknown began. They instinctively grasped a profound truth we are still wrestling with today, that reality has a limit, a shore beyond which lies something utterly different. It is astonishing to realize how these ancient intuitions find eerie echoes in our most advanced physics. The Norse world tree, with its separate realms, resonates with the idea of a multiverse, a cosmic tree with countless branching realities. The vision of a flat Earth under a dome is not so different from our modern picture of a three-dimensional brane universe, a vast, flat expanse of reality floating within a higher dimensional bulk. And that primordial ocean of chaos, it is a hauntingly accurate metaphor for the inflationary void, the seething, energetic sea in which our universe bubble first formed and still floats. Our ancestors imagined the cosmos supported by pillars. We calculate the mathematical constants that hold space-time itself together. They spoke of a great serpent encircling the world. We map the cosmic microwave background, the glowing remnant of creation's first light that wraps around us. The language has changed from poetry to mathematics, from gods to quantum fields, but the fundamental question remains stubbornly the same. What lies beyond the last pillar? What is outside the turtle? We have simply traded mythological imagery for theoretical models, yet we are still telling stories about the edge. This continuity across millennia reveals something profound about our place in the cosmos. We are the universe become conscious, trying to understand its own boundaries. Our drive to map the void is not just scientific curiosity. It is an ancient storytelling instinct, a refusal to accept that the story simply ends. The profound silence we encounter at the edge of our universe finds a chilling parallel in the silence we hear when we listen for others. This is the Fermi paradox, a simple question with terrifying implications. If the cosmos is so vast, so ancient, and so filled with the ingredients for life, why have we found no trace, no signal, no artifact of another civilization? The numbers scream that we should not be alone. With hundreds of billions of stars in our galaxy alone, many billions of years older than our sun, it seems statistically inevitable that intelligence should have arisen elsewhere and likely far earlier than us. They would have had eons to expand, to build, to make their presence known across the galaxy. And yet, the sky is quiet. This cosmic silence is not just an absence of radio signals, it is a profound mystery that may be intimately connected to the very boundaries we have been exploring. Perhaps the answer to where everybody is lies not in the stars themselves, but in the nature of the frontier. One unsettling possibility is known as the Great Filter. This idea suggests that the evolution of intelligent, spacefaring life requires passing through a series of incredibly difficult steps, from the formation of stable planets to the origin of life, the leap to multicellular complexity, the development of technology, and the avoidance of self-destruction. The Great Filter is a hypothetical barrier, a step so improbable that it prevents almost every potential civilization from progressing beyond it. The terrifying question for us is, where does this filter lie? Is it behind us, meaning we are a miraculously rare fluke that somehow passed a near-impossible early hurdle, like the origin of life itself? If so, we might truly be alone or nearly alone in this immense void. But the more haunting prospect is that the Great Filter lies ahead of us. It could be a universal bottleneck that every advancing civilization eventually hits and none survive. This could be something inherent to technological maturity, like the inevitable creation of self-replicating nanotechnology that consumes everything, or artificial intelligence that turns on its creators, or the discovery of a physics so dangerous it unravels reality itself. In this view, the silence is the sound of countless civilizations reaching a certain point on their journey and then vanishing, their lights blinking out one by one. Our search for an edge, then, might be a search for the wall that every civilization eventually hits, a boundary not of space but of survival. Another idea connects directly to the concept of cosmic isolation. What if we are not just alone but deliberately isolated? This is the zoo hypothesis, or the idea of a cosmic quarantine. Imagine a galaxy teeming with ancient, advanced civilizations who long ago established a kind of interstellar protocol. They have agreed to set aside certain regions, like our solar system, as protected preserves or observational zones, allowing younger species like ours to develop naturally without interference. To them, we might be a living museum exhibit, a cosmic national park. They watch, but they do not make contact, adhering to a strict prime directive to avoid cultural contamination. In this scenario, the edge of our observable reality is not just a physical horizon, it is a sociological one. The great attractor and the vast flows of galaxies could be irrelevant. The true boundary is a cloak of invisibility, a sophisticated technology that hides their presence from our primitive senses. The silence is not empty, it is curated. We are peering out from our cage, wondering why the zoo seems so empty, unaware that the walls are one-way mirrors. These theories force us to confront a humbling possibility. Our entire search for an edge, for a boundary to reality, might be framed by a fundamental immaturity. A civilization that has mastered interstellar travel or higher dimensional physics would not perceive the cosmos as we do. The limits of light speed, the vastness of galactic distances, the very concept of an observable horizon, these might be problems that a sufficiently advanced culture has long since solved or transcended. What we perceive as an impenetrable edge, a cosmic shore we can never cross, might be to them a trivial barrier, a line in the sand easily stepped over. The true structure of the universe, with its potential branes, bubbles, and bulk dimensions, might be navigable to those who understand its deeper rules. In that case, the silence could mean we are like ants in a vast forest, diligently mapping the blades of grass and grains of soil around our hill, completely unaware of the highways and cities that exist on a scale we cannot perceive. The Fermi paradox then becomes a paradox of perspective. We are listening for radio signals while they might communicate through quantum entanglement in the fabric of space-time itself. We are looking for Dyson spheres while they might harness energy from dark matter or the quantum vacuum. Our methods of searching are, by definition, primitive. We are shouting into a canyon with a tin can telephone, wondering why no one answers, while all around us a conversation is happening on a network we cannot access. The search for an edge and the search for others are ultimately the same quest, a drive to understand our place in the totality of existence. The cosmic silence is the loudest data point we have. It tells us that either life is astonishingly, heartbreakingly rare, or that the universe is structured in a way that actively prevents civilizations from ever meeting. The boundaries we have mapped, the horizons of light and causality, might be the very walls of our cage, whether built by nature or by unseen wardens. As we push our telescopes to their limits, straining to see the first light of the cosmos, we are also listening for a whisper that may never come. The void beyond the edge may be filled with wonders, or it may be filled with the silent graves of those who came before us, a cemetery of possibilities that stretches to infinity. Science gives us equations and evidence, but art gives us the vision to ask the question in the first place. Long before our telescopes could map the cosmic microwave background, human creativity was already charting the ultimate frontier, building conceptual maps of what might lie beyond the last star. These artistic visions are not mere fantasy. They are the necessary companions to scientific discovery, giving form to our deepest cosmic anxieties and hopes. Consider the medieval model of the cosmos, with Earth at the center surrounded by nested, transparent crystal spheres that held the moon, the sun, and each planet, all rotating in perfect harmony. The outermost sphere was the primum mobile, the first mover, and beyond that lay the empyrean heaven, the unmoving realm of God and the angels. This was a universe with a literal, physical boundary, a shimmering wall between the created order and the divine infinite. It provided a complete, comforting answer, a place where the universe ended and something else, something greater, began. That human need for a comprehensible edge, for a wall we can point to, has never left us. It simply changed its form. In modern fiction, the edge becomes a sociological or political limit. Isaac Asimov's Foundation series presents a galactic empire that encompasses the entire Milky Way. For its citizens, the edge of the galaxy is the edge of known civilization, a psychological barrier as much as a physical one. The mystery lies not in what's beyond the stars, but in what happens when that vast, stabilizing empire crumbles, leaving the periphery to fade into silence and legend. Here, the frontier is about the fragility of knowledge and order against the void. Then there is the enigmatic monolith in Arthur C. Clarke's 2001: A Space Odyssey. It is not an edge but a marker, a signpost placed by unseen architects. Its perfect, unnatural geometry screams that the universe has a design, and that there are builders who operate on a scale that dwarfs human history. The monolith represents a different kind of boundary altogether, the threshold of a new stage of evolution. It suggests the ultimate frontier might not be a place we travel to, but a state of being we are pushed toward by forces we cannot comprehend. These stories do more than entertain. They provide the conceptual vocabulary for our scientific quests. The crystal sphere finds its echo in the cosmic horizon, a boundary to perception. The edge of the galactic empire mirrors our own fears about the great filter and cosmic isolation. The monolith embodies the tantalizing possibility that the anomalies in our data, like the cold spot, might be artifacts, deliberately placed clues. Artists and writers externalize our collective wondering, turning abstract fear into narrative, giving us characters who stand at the brink so we can vicariously peer over with them. They ask the questions that science must then try to answer with data. Is the universe finite or infinite? Is it alone or part of a community? Does it have a purpose or is it silent? Every spaceship venturing into the unknown in a film, every map of a fictional realm that ends with "Here be dragons," is a rehearsal for our own existential exploration. These creative acts acknowledge the terror and the beauty of the unknown, and in doing so, they grant us the courage to keep looking up at the silent sky and asking, what is really out there? The ultimate silence may be our current reality, but human ingenuity refuses to accept it as a final answer. Our future may hold tools that could, in essence, allow us to cheat the cosmic horizon, not by traveling faster than light, but by using the universe's own strange rules to peer around the corner. One of the most promising and bizarre possibilities lies in the phenomenon of quantum entanglement. This is the mysterious connection between particles where the state of one instantly influences the state of its partner, no matter how far apart they are. It is as if two coins, flipped in different galaxies, always land showing the same face, a connection that seems to defy the cosmic speed limit of light itself. While we cannot use this to send information faster than light, some physicists speculate that the fabric of space-time on the largest scales might preserve subtle quantum correlations from the universe's earliest moments. These correlations could be imprinted on the cosmic microwave background in ways we are only beginning to understand. By building impossibly sensitive detectors, a future civilization might learn to read these quantum whispers, these faint echoes of connectivity that predate the horizon itself. It would be like listening to the faint, entangled vibrations in the foundation of a building to deduce the shape of rooms that have been sealed off forever. We would not be receiving light from beyond the horizon, but inferring its structure from quantum memories etched into the space we can see. This would not be a telescope, but a quantum seismograph for the cosmos, feeling for tremors from the other side of the veil. Even more radical is the prospect of manipulating space-time itself. If the fabric of the cosmos can be stretched by dark energy, could it, in theory, be folded or shaped by a technology of inconceivable power? The theoretical constructs of wormholes and warp drives, often relegated to science fiction, are grounded in the real mathematics of general relativity. They require forms of matter or energy with negative density, something we have not yet discovered or created, but a civilization that mastered the energy of stars or even galaxies might embark on engineering projects of cosmic scale. They might not send a ship to the edge, they might bring the edge to them by gently warping the local geometry of space to create a lens, a window that bends light from behind the horizon into view. It would be the ultimate periscope, not looking out but looking around the curvature of the universe. Such feats are far beyond our grasp, perhaps forever beyond the laws of physics as we know them. Yet they represent the logical endpoint of a species determined to see what lies beyond its cage. This drive could culminate in a project of such staggering scale it redefines the purpose of existence. Imagine a civilization that survives for trillions of years, that has spread across the stars and harnessed the energy of every galaxy within its reach. Having conquered scarcity and perhaps even mortality, faced with the cooling and darkening of the cosmos, what would be its final grand endeavor, the ultimate project might not be exploration but comprehension. Such a civilization might dedicate all its accumulated knowledge and energy to a single, universe-ending computation, using the last stars as fuel and the structure of spacetime as a processor. It would attempt to run a simulation of such fidelity and scale that it models the entire history of the cosmos from its first moment to its last. The goal would be to answer the questions that haunted it from its primitive beginnings, to run the experiment of existence backwards and forwards, testing every model of the multiverse, every theory of the Big Bang, every possibility of what lies beyond the observable horizon. In this final act, the civilization would not be trying to escape the universe, but to understand it completely, to turn the cosmos into a mirror to study its own origin and its ultimate boundaries. The energy required for this final computation would be the last flash of light and thought in a dying cosmos. It would be the universe through its most complex creation, finally turning its gaze fully upon itself, seeking the answer to the only question that ever truly mattered before the eternal night falls. The journey to the edge is, in the end, a journey back to ourselves. We have charted horizons of light and causality, dreamed of bubble universes and cosmic simulations, and measured the silent pull of dark energy. Each theory, from the infinite to the illusory, paints a portrait of a reality far stranger than our ancestors could have conceived. Yet, amidst this staggering scale, a quiet, personal question remains. What does any of it mean for you, sitting here in this fleeting moment of conscious life on a pale blue dot? The sheer vastness can feel crushing, reducing our hopes and struggles to cosmic insignificance. But there is another way to see it. That profound human urge to look up and ask what lies beyond the last star, That relentless curiosity that built our telescopes and crafted our myths is not a symptom of our smallness. It is the signature of our significance. We are the universe's way of knowing itself. The atoms forged in the hearts of ancient stars are not just in us, they are us, and they have now arranged themselves into a pattern complex enough to wonder about their own origin. Your curiosity is the cosmos becoming self-aware. The question itself is the destination. For millennia, this single inquiry has been the engine of everything noble in our species. It drove early navigators to sail past the known horizons, fearing they might fall off the edge of the world. It pushed scientists to decode the mathematics of gravity and the language of light. It inspired artists to fill the unknown with gods, monsters, and galaxies, giving shape to the void. Whether the answer is an infinite multiverse or a finite, lonely bubble, the act of searching for it defines who we are. We are the creatures who build periscopes to peer over the walls of our own perception. So, the next time you feel overwhelmed by the scale of it all, remember this. Your wonder, your drive to understand your place in this grand story is not a small thing. It is the most human thing possible. It connects you to every stargazer who ever lived, to every thinker who dared to map the unknown. In asking what lies beyond the edge, we are not just seeking a boundary. We are declaring that we are here, that we are awake, and that we refuse to accept the silence as a final answer. The universe may be ancient and vast, but it took 13.8 billion years to make a question, and you are holding it. We have sailed across an ocean of ideas, from the shores of our observable universe to the strange seas beyond. Our journey revealed that the edge is not one thing, but many. It is the horizon of light, a permanent curtain drawn by the expansion of space. It is the question of shape, a flat geometry hinting at infinity, or a colossal hypersphere that curves back on itself. We have confronted the multiverse, a frothing sea of bubble universes, each with its own laws, forever out of reach. We have weighed radical possibilities, from holographic projections and simulated realities to the notion that the final frontier is the very limit of our own consciousness. The answer remains elusive, hidden behind veils of causality and time. Yet, this is not a story of failure, but of profound success. The value of this quest lies not in a final destination, but in the journey itself. Every theory, every measurement, every leap of imagination expands the map of human understanding. It pushes the boundaries of what we believe is possible, challenging us to think in scales and dimensions that defy everyday intuition. We may never build a ship that sails past the cosmic horizon. We may never receive a signal from a neighboring bubble universe or find the exit code in a simulated reality. But in daring to ask the question, we perform the most human act of all. We take our place in a long lineage of explorers, using the tools of science and the power of story to chart the unknown. The universe might be silent, but our curiosity echoes across the ages. So we leave you with the question that started it all, the one that now belongs to you. What do you think is out there? Let us know in the comments, and do not forget to subscribe for more journeys to the edge of reality.